imagine your computer. It's got its super fast brain, the processor.
Right.
And then it's got its memory, like this huge library of information. But here's the kicker. Every single time the brain needs something from that library, it has to send out like a little messenger. This messenger has to run to the library, find the info, bring it all the way back, brain processes it, and then sends it back again.
And that round trip, it's happening constantly.
Yeah.
Billions of times a second, maybe.
Exactly. And it's not just slow, relatively speaking. It's a massive energy hog, just wasteful. So what if? What if the library itself could think? What if it could process that information right there on the shelf? No messenger needed.
That would change everything.
Well, that's not science fiction anymore, is it? Today, we're doing a deep dive into exactly that kind of technology. It's revolutionizing how computers work. We're talking about in-memory computing, and it's powered by something really innovative called phase change memory.
Yeah, PCM. It's fascinating stuff.
Our mission today is basically to unpack this breakthrough. We want to understand, the core ideas and explore how it could seriously transform everything, like from the AI in your phone to maybe even how we build probes for deep space.
Big implications.
And we're grounding this discussion in some serious research. We're looking at a really comprehensive review article. It's titled Phase Change Memory for In-Memory Computing. It was published in Chemical Reviews in their special issue on neuromorphic materials, which is a top-tier journal.
And the authors are Ghazi Sarwat Syed, Manuela Gallo, and Abu Sebastian. They're all doing pioneering work at IBM Research Europe.
Okay, so let's unpack this core problem first. This processor-memory divide.
Right.
In almost all our computers today, the ones in our pockets, on our desks, the brain, the CPU, and the memory, they're physically separate components.
Different chips, sometimes even different parts of the motherboard.
So like that messenger running back and forth, data is just constantly shuttling between them. It creates this huge bottleneck. It's like a digital traffic jam, right? Waste time, waste energy.
Exactly. And what's truly fascinating, or maybe frustrating, is how much this bottleneck limits us. It's not just about making your app load a fraction of a second faster. It's a fundamental physical barrier. It holds back computing efficiency, especially for the really data-heavy stuff we're doing now. Think about AI.
Oh, yeah. Massive amounts of data.
Right. Training an AI model, or even just running one to, say, recognize your voice or understand a picture that involves moving and processing just vast quantities of data, it really is like trying to drink from a fire hose through a tiny straw sometimes.
Good analogy.
So it really forces the question, can we make the memory itself smarter? Can we, cut out all that travel, bring the computing right to the data?
And that is precisely where phase change memory, PCM, comes into the picture. It's potentially the game-changing solution. It's that smart filing cabinet we were talking about. See, PCM is this revolutionary type of memory. It doesn't store information just by holding an electrical charge, like most RAM. It stores data by actually changing the physical state of the material itself.
It's kind of like, remember those old rewritable CDs or DVDs, how the laser changed the surface?
Yeah.
It's conceptually similar, but happening at a microscopic, nanoscopic level inside the material.
So what's the material? How does that work?
Well, the core concept is actually wonderfully elegant. PCM uses these special materials, usually alloys called chalcogenides. The most famous one is G2SB2TT5. Everyone just calls it GST.
GST. Got it.
And this GST material can be switched back and forth reversibly between two different physical states or phases. One state is amorphous, it's disordered, kind of glassy, and it has high electrical resistance, doesn't conduct electricity well.
Okay, like an insulator almost.
Sort of. And the other state is crystalline. It's highly ordered, structured, and has low electrical resistance. It conducts electricity much better.
So high resistance state, low resistance state.
Exactly. It's like a tiny, tiny physical switch.
Right.
And you flip it between these states using very precisely controlled pulses of heat, usually generated by passing current through it.
Okay, here's where it gets really mind-bending. And this is a key point from the work by Syed, Legallo, and Sebastian at IBM. Imagine a memory technology that isn't just fast. I mean, writing data in tens of nanoseconds.
Which is incredibly fast.
But it's also really stable. It can hold on to that data, that physical state, for potentially up to 10 years at room temperature without power.
That combination is just amazing. Speed and permanence, non-volatility, that's sort of the holy grail for memory.
It really is. And this allows for devices that can learn and operate continuously without losing information when the power's off.
And it's funny, there's a bit of history here. For a long time, the sort of prevailing wisdom in semiconductor physics was that you needed perfect crystals, really ordered materials to make functional devices.
Right, that makes intuitive sense.
Yeah. But back in the early 1960s, some really groundbreaking research looking into these chalcogenide glasses, the same family as GST, completely challenged that idea. They discovered these seemingly disordered glassy materials could actually be switched between states electronically. That discovery basically paved the way for PCM decades later.
Wow. So challenging old assumptions led to this. Okay, so it stores data by changing its physical state.
Yeah.
But how does it compute? That's the in-memory computing part.
This is where it gets really interesting, like you said. With IMC, these PCM devices aren't just sitting there storing zeros and ones. They're actively taking part in calculations. Right there, inside the memory chip.
Now, what properties allow that?
Well, the IBM Research Europe team, in that chemical reviews paper, they detailed two key properties that PCM leverages brilliantly for this. The first one is multi-level conductance.
Okay, multi-level, what does that mean?
Think about standard computer memory. It's binary, right? It's like a basic light switch, either on or OFF, a 1 or a 0. PCM, though, is more like a dimmer switch. Because you can control that transition between amorphous and crystalline very finely, you can actually create a whole range of states in between fully amorphous and fully crystalline. Each of these intermediate states that has a distinct electrical resistance or conductance level.
Ah, so it's not just on, and, or OF, it's like
Yeah.
levels 1 through 10 or even more.
Exactly. A whole spectrum of values can be stored in a single PCM cell. And this is absolutely crucial for AI. Deep neural networks, the algorithms behind most AI, they rely on something called synaptic weights. These are basically numbers that represent the strength of connections between artificial neurons.
And those weights aren't just 0 or 1, they're graded values.
Precisely. So a single PCM device with its multi-level capability can directly store one of these complex synaptic weights. It encodes a much more nuanced piece of information than just a simple yes-no.
Okay, that's one property. Multi-level conductance. What's the second?
The second key property is its accumulative nature.
Accumulate.
Yeah, think about it like carefully adding drops of water to a measuring cup. You can gradually change the conductance state of a PCM device by applying a sequence of identical electrical pulses.
So each pulse nudges the state a little bit further along that spectrum.
Exactly. You can incrementally increase or decrease the conductance. This allows you to perform calculations like addition or multiplication directly within the memory device itself, step by step. You're literally accumulating the result in the physical state of the device.
Wow. Okay, so you've got the dimmer switch for storing complex values, and you've got this ability to sort of add to the state with pulses.
Put those together and you can see the bigger picture. This whole approach, IMC with PCM, it basically gets rid of that constant, frustrating back and forth data shuffling between processor and memory.
Right, the messenger is fired.
Ha, pretty much. And the energy savings are just enormous. We're talking about performing basic AI operations using femtojoules of energy.
Yeah.
That's an unbelievably tiny amount. Think about battery life in mobile devices.
Incredible. And faster, too, presumably.
Oh yeah, drastically faster for certain tasks. Because you're not waiting for data to travel. You're doing the math right where the numbers live, like doing calculations directly on the page of a book instead of copying numbers to a separate calculator and back again. It massively boosts efficiency for AI, pattern recognition, all sorts of data-intensive things.
Okay, this sounds almost like magic. Let's peek under the hood a bit more at the materials science. What makes these specific materials, these chalcogenides like GST, work so well?
It's a fascinating area. The authors of the review highlight three really crucial characteristics. First, you need a big difference, a significant contrast in the electrical properties between the amorphous, high resistance, and crystalline, low resistance states. That contrast is what lets you clearly distinguish a 0 from a 1 or different levels in between.
Makes sense. You need to tell the states apart reliably.
Second, you need really rapid transitions between these states. We're talking nanoseconds. That's essential for high-speed operation.
Fast switching. Got it.
And third, and this is maybe a bit counterintuitive, you need the states themselves, once programmed, to be highly stable at room temperature, even though they can switch super fast when you want them to. That's the data retention part, the 10-year thing.
Right. Fast change when you trigger it, but stable otherwise. How do they manage that combination?
That's where the weird and wonderful, as you put it, comes in. One really unique aspect the IBM team discusses is the fragility of these phase change materials.
Fragility. Like they break easily.
No, not in that sense. In material science, fragility describes how quickly a liquid's viscosity, its resistance to flow changes as you cool it down towards its glass transition temperature.
Okay, like comparing honey and, say, molten silica glass.
Exactly. Silica is a strong liquid. Its viscosity changes gradually and predictably as it cools. But materials like GST behave like fragile liquids, more like organic polymers or, yes, thick honey. Their viscosity changes dramatically over a very small temperature range near the freezing point.
And why is that important for PCM?
It's absolutely crucial. This high fragility means you can cool the molten material so rapidly after heating it, the melt quench process, that the atoms don't have time to arrange themselves into an ordered crystal. They get frozen in place in that disordered amorphous state. But it also means that if you heat it just right, below the melting point but above the glass transition temperature, those same fragile liquid dynamics allow the atoms to rearrange themselves very quickly into the stable crystalline state. That rapid change in viscosity is key to both fast amorphization and fast crystallization.
Wow. So the material's fragile nature is actually its strength here.
Precisely. It enables those nanosecond transitions. The paper gives numbers like liquid GST has a fragility value around 90, while strong liquids like silica are below 20. It's a big difference.
Okay, anything else unique about how these materials behave?
Yes, there's another really important electrical property called threshold switching.
Threshold switching.
Remember how the amorphous state has high resistance? Well, if you apply a specific voltage across it, the threshold voltage, it suddenly dramatically switches to a highly conductive state, almost like flipping a switch electrically, even before the structural phase change happens.
So it kind of triggers itself.
In a way, yes, it acts like a self-triggering switch. This is essential because it allows you to select and activate specific memory cells in a large array without accidentally disturbing the neighboring cells. This nonlinear snap in conductivity is vital for making PCM practical in dense memory chips.
Okay, this technology sounds incredibly promising, but, nothing's ever perfect, especially when it's new. Are there challenges, hurdles to overcome?
Oh, absolutely. Like any cutting-edge technology, especially one trying to do computation with analog physical states, PCM devices face what researchers call non-idealities. These are basically small imperfections or variations in behavior that can affect the precision of those analog computations.
Makes sense. What kind of imperfections are we talking about?
Well, one major one is conductance drift. Remember how we set that dimmer switch to a specific level?
Yeah.
Well, with PCM, particularly in the amorphous or intermediate states, that programmed conductance level isn't perfectly stable. It can slowly, gradually change or drift over time. The resistance tends to increase logarithmically with time.
So the value you stored drifts. Like a stored 7 might slowly become a 6.5.
Exactly. The paper gives an example. A device reading 200 microsiemens right after programming might drift down to maybe 71 microsiemens after 1,000 seconds. It follows a power law with a drift exponent typically around 0.1 to 0.15 for GST. It's predictable, but it needs to be accounted for.
Okay, that sounds like a problem for precise calculations. What else?
Then there's just random noise. Like static on a radio, the conductance readings can fluctuate randomly by small amounts from read to read.
Standard electronic noise, basically.
Yep. And temperature sensitivity. Small changes in the chip's operating temperature can affect the conductance, especially of the amorphous state. Its resistance changes more significantly with temperature compared to the crystalline state. The paper mentions activation energy is about 0.2 to 0.3 electron volts for amorphous GST compared to maybe 0.04 to 0.12 for crystalline.
So if the chip heats up a bit during operation,
your stored values might shift slightly, introducing errors. And finally, there's something called polarity dependence.
polarity, like positive and negative.
Yeah. Ideally, the device's resistance should be the same regardless of whether you're applying a positive voltage or a negative voltage to read it. But sometimes, due to tiny physical asymmetries in the device structure, the measured conductance can actually change slightly depending on the direction of the current. That can also lead to numerical errors in computations.
Okay, drift, noise, temperature sensitivity, polarity dependence. Those sound like pretty significant hurdles if you need reliable, accurate computation, especially for complex AI.
They absolutely are challenges.
So, this raises an important question, right? How are researchers actually dealing with these issues? Are they finding ways to make these devices accurate enough for real-world applications? Or are these problems going to limit where PCM can be used?
That's the crucial next step, and it's where some really clever device engineering comes in.
Yeah.
Researchers aren't just accepting these non-idealities, they're actively developing ingenious ways to mitigate them.
Like what?
Well, Take drift and noise. One really promising approach mentioned is using projected PCM devices. Ghazi Sarwat Syed, one of the review authors, has published work on this, for instance, in Advanced Functional Materials. The idea is to build the device with a special non-insulating liner material adjacent to the main phase change material. During the read operation, this liner essentially creates an electrical bypass, shunting the read current around the most drift-prone part of the amorphous region.
Ah, so you're sort of reading a more stable part of the device?
Exactly. You're projecting the stable resistance of the interfaces rather than reading through the bulk amorphous volume, which is the main source of drift and noise. It significantly reduces both issues.
That's clever. What else?
Another really cool technique involves using superlattice films. Imagine instead of just a single layer of GST, you stack up alternating ultra-thin layers of, say, GST and another material like antimony telluride. Each layer might be just a few atoms thick.
Like a nanoscale layer cake?
Pretty much. And work by researchers like Khan and others presented at places like the IE Symposium on VLSI technology shows that these superlattice structures create what's called electrothermal confinement. They help focus the heat and electrical fields more precisely during programming, which boosts efficiency, lowers the required energy, and also helps to reduce drift and noise effects.
So by engineering the device structure very carefully, they can tame some of these imperfections.
Exactly. These kinds of innovations are absolutely critical for making PCM-based IMC reliable enough for the really demanding computations needed in advanced AI and other fields. It's a very active area of research.
Okay, so we've talked about the problem, the solution with PCM, how it works, the challenges, and the clever fixes. Let's bring it back to the listener. What does all this actually mean for you? What's the practical impact?
Right. Why should you care about phase change materials and conductance drift?
Yeah. Well, it's about a fundamental shift in how our devices will compute. Think about traditional memory, like the RAM in your computer. Its main job is just storing binary data accurately and allowing very fast reads and writes.
Speed and fidelity for zeros and ones.
Exactly. But in memory computing with PCM, its priorities are a bit different. As the review paper highlights, the focus shifts towards maximizing compute operations per watt and per square millimeter. How much math can you do for the least energy in the smallest space? That's the key metric.
TOPS per watt, TOPS per square millimeter, tera operations per second.
Right. And IMC does this using that whole continuum of conductance states, not just binary. And interestingly, for some applications, especially things like running an already trained AI model, what they call inference IMC, might not need that 10-year data retention. Maybe just days or weeks is fine.
And maybe it doesn't need billions of write cycles like flash memory. Perhaps hundreds of thousands are enough for inference tasks. Table 1 in the paper actually lays out these different requirements quite nicely.
So it's a different set of trade-offs, optimized for computation rather than just storage. And this opens up some incredible application possibilities that are going to touch almost everything digital.
For sure. The most obvious one is deep neural network inference, making AI faster and way more energy efficient, especially AI running locally on your devices at the edge.
So better AI on your phone, in your smart speaker, your watch, your car, without draining the battery nearly as fast.
Exactly. Things like computer vision, understanding speech, translating languages, all happening more efficiently right on the device.
And you mentioned sensors before.
Yeah, imagine computational sensors. Like a camera sensor where the pixels themselves, using PCM, can perform calculations directly on the light they capture. Real-time image processing right at the source. Syed and the team discussed this in a paper in NPJ Unconventional Computing, turning raw sensor data into useful information instantly.
That's wild. What else?
Well, there's cryptography. Using the inherent randomness and analog nature of PCM devices to potentially enable more secure data encryption or even generate random keys for security right inside the memory. There's research on this, like work by Kovacs and colleagues published in Philosophical Transactions A.
So memory that helps keep data safer. Interesting.
And think about AI learning. There's the idea of memory-augmented neural networks. Using PCM's ability to store information long-term could allow AI systems to learn continuously, adding new knowledge without catastrophically forgetting old stuff. That's a huge challenge in AI today, and PCM could be part of the solution.
It's lifelong learning for AI.
And if we look really far out, there's even photonic computing, using light, photons instead of electrons to interact with phase change materials. Work by Rios and others, published in Science Advances, has shown possibilities here, potentially leading to incredibly high-speed, light-based computation within memory.
Wow, so the applications really span from making today's AI better to enabling completely new forms of computing.
Absolutely. The potential impact is huge.
So looking ahead then, where does this technology stand? How close is it to being mainstream?
Well, Syed Gallo and Sebastian, in their review, make the point that PCM is arguably the most mature of these emerging memoristive or resistive memory technologies for in-memory computing. It's had decades of development, partly driven by its potential use in storage memory as well.
So it's further along than some other competing ideas.
Generally, yes. They mentioned that prototype chips integrating TCM for IMC have already been built, some incorporating up to, I think, 35 million PCM devices. That gives them the largest computational weight capacity demonstrated so far among IMC accelerator chips. That's a significant milestone.
Okay, so it's definitely moving beyond just the lab. What's next? What needs to happen to really push it forward?
The path forward seems to involve progress on two main fronts. First is increasing compute density. That means making the individual PCM devices even smaller and figuring out how to stack multiple layers of these memory arrays vertically in 3D. More computing power in the same chip area.
Packing more thinking power in.
Right. And the second front is improving compute precision. That means continuing to develop new device structures and materials, like those projected PCM devices we talked about, to get even lower drift, less noise, and minimal sensitivity to temperature changes, making the analog computations more reliable.
So denser and more accurate.
Exactly. The ultimate dream really is to create fully integrated, on-chip neural processing units. These would combine PCM arrays with the necessary control circuits right on the same chip, bringing really advanced AI capabilities directly to everyday low-power edge AI devices. Think tiny microcontrollers in sensors or appliances. And then from there, scaling up these architectures to build larger, more powerful standalone accelerator chips for data centers and cloud computing environments.
So starting small and local, then going big.
That seems to be the trajectory.
Okay, so let's try and wrap this up. What are the big takeaways from our deep dive today?
I'd say there are three key things. First, we're facing a fundamental bottleneck in computing, the processor-memory divide. And in memory computing is a radical approach to overcome it by bringing computation to the data.
Right, stop the shuffling.
Second, phase change memory, PCM, is a really powerful enabling technology for this. Its ability to change physical states, store multiple levels, and accumulate values allows memory to actively participate in computation, offering huge gains in speed and energy efficiency.
The memory that thinks.
Pretty much. And third, while there are definitely challenges like drift and noise, researchers are actively developing clever solutions, and this technology isn't just theoretical anymore. It's finding its way into prototype chips and enabling real breakthroughs, especially in AI.
It feels like we're on the cusp of a pretty significant shift in how computers are built and what they can do.
I think so too. It's a really exciting time in computer engineering and material science.
So here's a final thought for you, our listener. As our devices become capable of essentially thinking right inside their own memory, moving beyond just storing and retrieving, what new forms of intelligence, what new kinds of interaction, what new applications, maybe even what new forms of creativity will you imagine and maybe even create with them? This shift from memory just holding data to memory actively computing feels like a truly monumental leap. It really could redefine the boundaries of what technology can achieve.